We have about 65 participants. I think this is a good enough time to start. So welcome everybody who are online for this two-part lecture series on numerical modeling of astrophysical flows. Now, I specialize in doing simulations of astrophysical flows and applying it to various kinds of scenarios to study astrophysical systems. And what the organizers have asked me is to give you some basic idea of the numerics involved in it, so that you can get a flavor of what are the technical things that we need to follow when we do simulations. So I have designed the lecture in two parts. The first, I'll give you some basic idea of, firstly, what is meant by simulation, and what are the basic equations we solve in fluid dynamics when we do astrophysical simulations of astrophysical flows, the basics of the numerical scheme of one type of simulation, and I'll give you some few examples of the results of some of the simulations that we've been doing, and that's for the first lecture. In the second lecture, I will introduce you to one software or code called Pluto, which is a very versatile open source code, which I have been working on for a long time, and I'm one of the co-developers now. So I'll give you a brief introduction to Pluto, show you how to install it and run it. It's quite simple to use, but difficult to master, so that you get an idea that working on simulations is not a daunting task, and it can be done by anybody, but you have to keep certain basic principles in mind. Otherwise, you'll get distracted into certain fallacies and numerical instabilities, which you may not be able to understand. So I'm sharing my screen and starting the slides. If you have any questions, I would request you to write in the chat. I will read through the questions at the end, and then I will call upon you, ask you to raise hands at the end and take your questions later on. So numerical modeling of astrophysical flow. So when we talk of simulations, what we really want to study is how the different matter all around us behave and interact with one another in different kinds of astrophysical environments. So as we all know, that matter around us is actually based on particles, small particles, atoms and molecules that are moving about and interacting with one another. So the basic fundamental level of simulation that one can do is actually simulate the motion of the particles themselves. Now, if you take a simple box, you'll have billions and billions of particles in them, or atoms and molecules, and of course we cannot simulate the motion of all the atoms and molecules even in a small room, let alone the size of a solar system. So what we usually end up doing is we take a bunch of particles and call them a superparticle and follow the motion and evolution of these particles. Now, where are these kind of particles simulations used? They are used, for example, in modeling the motion of stars or stellar kinematics, modeling the motions of galaxies in very large scale simulations of the size of, say, few megaparsecs, few tens of megaparsecs as well. What they do is each of the galaxies themselves are like point particles. There are billions of galaxies. And we have to understand and follow the evolutions of all these billions of galaxies and how they interact under the force of gravity. So those are large-scale simulations where the galaxies themselves are like treated as particles. But even on smaller scales, you have had lectures by Nishant, who has, I'm sure, described to you the basics of fluid dynamics and plasmas. So we can also do particle-based simulations on plasmas. So we follow the evolutions of electrons and protons in the presence of electric and magnetic fields, and how for example, these charged particles are accelerated by the electric fields, or in the presence of magnetic fields, how they gyrate along the magnetic fields. All of these we can follow in particle-based simulations. So what are the basic challenges of particle-based simulations? The basic challenge is this fact that there are many body interaction. The large-scale particle simulations usually consider 1 billion particles. as I said, the particles can be considered as stars, where the interaction between them is purely due to gravity. The particles can be ions and electrons, where the interaction is mostly electromagnetic. But if you have billions of particles, then you have to account for the many body interactions. So each particle is not just interacting with its nearest neighbor, but many particles all around it. Maybe not all of the particles in the box, because there are certain length scales beyond which the interaction decays, but it's still undergoing many interactions. So billions of particles, and for each particle you have multiple interactions. So you can understand the level of complexity increases vastly. And also, another challenge in this particle simulation is you have to resolve the length scales of the dynamics of the particles. So usually when we talk of, say, large scale system, the individual particle motions are quite small. So for example, let's say you take the air in the room. Now the heat in the room is guided by the dimensions of the room. So if you have one side of the room that is hot, the other side, the temperature will increase due to convection, and that the length scale of this convection process is guided by the length scale of the room. However, the convection is carried out due to motions of the particles in the room, the molecules. And the typical mean free path of the molecules is of just a few angstrom. That's 10 to the minus 10 centimeters. So you can understand that if you have to resolve the dynamics of the particles, you have to go to much smaller length scales. And if you restrict yourself to much small length scales, understanding things happening at much larger length scale, for example, the length of the room itself, when you're talking of dynamics of individual atoms, becomes really challenging, because you have to follow the evolution up to several orders of magnitude of length scales. So that is a demanding task. So many of the times, for example, when we do the particles simulations in plasmas, what we actually do is not model the entire system, but model just a small part of the system, where we can actually resolve the individual motion of the electrons and protons. So that is called the gyro radius. So the length scale of which the electron is moving around in circles around the magnetic fields, or gyrating along the magnetic fields. So we have to resolve this gyro radius, and typically the length of the simulations, of length after which we can follow the evolution of the particles, is a few 10 times or a few 20 times the gyro radius of the particles. Very large scale simulations can do 100 times or 1,000 times the gyro radius of the particles, but that is pushing the limits. So that is a big challenge of the particle simulations, to resolve the dynamics of the particles on the scales at which they're moving, and then follow their evolution on very large scales. Now, on the other hand, we can do fluid simulations. So as I said, the air in the room is composed of atoms and molecules. However, you can see that what we can look at the air and think of it as a continuous distribution of gas all around us. So that is a fluid. So when we talk of very large scale, we can approximate the particle behavior of the gas and talk of it in terms of an average distribution of some quantities. And this is really applicable when the particle mean free path, it's much smaller than the physical dimensions. So essentially, what from the large scale point of view, what you see is not individual particles, but collection of particles or densities of particles. A number of particles are per unit length scales, per unit volume. So we replace the particle nature by a continuous distribution of some quantity, which is the pressure of the gas, the density of the gas, the velocity of the gas. So essentially, we start from a particle behavior and move to a gas behavior. Now, in standard plasma physics, there are relations where you take the kinetic equations of the particles and integrate over them in volume, and have to apply some closure principles, and then can derive the fluid equations of the. And I think Nishant must have taught you this in the fluid lectures. So in the fluid simulations, what we actually evolve is the mean properties of the gas and how they vary locally at different spatial locations, as well as how they evolve with time. The main problem or the main challenge of the fluid simulation is achieving sufficient resolution to reduce numerical dissipation. So what we do in this fluid simulation is we take again, the example of the room. We divide the room into small compartments or small grids and study the evolution of the fluids over this grid. Now, because you are taking a continuous distribution of matter and discretizing it into small sections and then just replacing that small section with an average quantity, you are losing information. And this induces numerical dissipation, so artificial viscosity or dissipation into your systems. So that is a big challenge. So if you want to say study the length of the room, you have to divide the room into finer, smaller boxes and study the evolution of, this will become a bit more clear as I give some examples later on of how you form the grid. But the finer your choice of the resolution of your grid, the better you are in understanding the true effects of the physical systems and not dominated by numerical effects or artificial effects. And the artificial effects come from the very fact that you're taking a continuous distribution of gas and discretizing it into small compartments. Another problem with the fluid simulations or this kind of a grid-based simulation is the assumption of geometry. Suppose you have a spherically evolving gas or shell of gas. Now you try to simulate that on a Cartesian geometry. So inherently your problem, the physics of the problem is spherically symmetric in nature, but you have square boxes over which you are trying to compute these quantities. That induces errors because you are not sampling fine enough. And these are some of the challenges we have to face. So the main difficulty is the resolution and the assumption of the grid geometry. So I will be mostly talking about the fluid simulations because that is what I do. Particle simulations themselves are a different kind, and we'll take another lecture. And I do not have the time to go into it. So before I go into the details of the lecture, one moment here. Details of the lecture. Just wanted to give you a flavor of what kind of numerical softwares or languages we use for the simulations. Now, I know that many of you who especially are currently undergoing bachelor's and master's training in different universities all have numerical courses in your curriculum. And many of the courses, what is mostly taught are these high-level languages and how to deal with some standard basics in numerical integration, matrix inversions, etc. And what you mostly are comfortable with are things like Python, MATLAB, IDL, not many maybe, etc. These are very good for quick analysis. They are good for visualization because you can write and solve something and then quickly plot it and visualize it. But these are slow and ineffective. For large-scale simulations, we usually use basic level languages like C, C++, Fortran, which are much faster. But also, again, these are still insufficient to run on a single computer. So based on the basic structure of C and Fortran, there are other kind of higher level languages, not higher level, the basic level languages, which can devise or instruct the computer program to run on multiple computers at the same time. So those are called MPI, or message passing interface. And MPI in C is called MPI-CC, in Fortran MPI F90, in C++ MPI C++. So what these do is we don't run things on a single computer. We have multiple processors connected by fast connectivity. It's called InfiniBand connectivity. And we divide the problem into small chunks, and each of the processors do the computation of that particular chunk. And then at the end of one time step, all the processors communicate with one another and share the solutions. And so as a whole, their entire solution evolves with time. So that is what is called distributed architecture, or distributing the job into multiple processors. And this is the most common type of high performance clusters that we have now. However, with the advancement of technology, we also have a new avenue of doing the simulations. We all have, we know that we have GPU cards on most desktops and laptops nowadays. And these GPU cards can also handle multiple operations at the same time because of threading of how the architecture is placed. And there is always the CPU interface, which can allow the local processor to send some operations onto the GPU card, let the GPU card process it and send it back to the CPU. So this vastly increases the efficiency. And this is also used. So in many of the current clusters, they're called hybrid clusters, where we have multiple processors connected by into fast connectivity. And each of these processors also have, each of these clusters of processors, let's say nodes, but let's not get too technical. Each of these processors also have a GPU card, where the main processor can communicate with the GPU card and further subdivide the operations, further increasing the speed up. So just to give you a typical example, the large-scale simulations that I have been doing, and many others, are typically run on 2,000 to 3,000 processors. Such kind of resources is actually quite difficult to obtain currently in India as well. The largest, IUCAA has a decent cluster with around 1,500 processors, but these are mostly run on large-scale international high-performance supercomputers. But these are the typical numbers that we do when we do cutting-edge numerical simulations. Okay, going to the next slide. Okay, so as I said, IUCAA, the basic infrastructure is having a high-performance computing facility. But also let me remind you, many of the simulations do not often require such really high-scale resources. The main thing that one has to focus on is what is the physics being put in. How does the physics behave in with respect to certain input parameters? So small-scale simulations can also be run on your desktop, or if you want to say study some basic principles, like for example, some fluid instabilities, like Kelvin-Helmholtz and Rayleigh-Taylor instabilities. I'll show an example in the next session. So all this can be done on a desktop. But for really large-scale challenging problems, we need large-scale facilities. So when you do large-scale simulations, the data volumes also become a big problem, because we have several gigabytes of data. And for the really large-scale simulations, large-scale data analysis sectors, it can also run into petabytes for the future missions that are planned. But the kind of simulations I involve in are several gigabytes, and then visualizing them and analyzing them itself requires a high-performance computer in itself, with a serious amount of memory. One important thing that we all have to focus on while doing this computing is the performance in a parallel environment. So suppose, which we call a scaling of the problem. So I've presented you cut up from the Pluto user guide, which shows two typical scaling plots. And this is something that we all have to demonstrate to the supercomputing facilities before we can run our programs. Because we have to show that our programs are efficient enough to run on large-scale facilities and will not use up and waste resources. So scaling is, you take your problem and divide it into different kinds of, into multiple processors. Now, as I said, these processors will have to talk to each other. So, and this passing of information from one processor to another is what is a bottleneck and prevents and reduces the efficiency. So how often you need inter-processor communication is what decides how efficient your code is. So often what we have to do is we take a typical problem and then run it on multiple processors and different numbers of processors, and see whether the time to the solution is actually decreasing. For example, if you look at the left-hand side of the plot, it is one particular problem, and what it has been shown is the time taken for the solution on the y-axis and the number of processors on the x-axis. As we increase from 1,000 processors to 10,000 processors, this is really done on a very large-scale supercomputer, the time taken by this problem decreases linearly in logs. So it's like a power law. And this is a very good sign which shows that as you increase your computational resources, your program can efficiently divide up the problem into smaller chunks without losing the efficiency, without losing the slope, which is good. There is no bottleneck, essentially. Otherwise, what might happen is, say, you go from 100 processors to 500 processors, and beyond that, you cannot run the program. There is no gain in efficiency. So there is no need to go to 1,000 processors, and you are stuck. So this is something that we all need to demonstrate. So that is called the scaling of the numerical codes that we have to test. Okay, so this was a big introduction to the basic essence of numerical simulations. So now I'll introduce the basic equations we solve when we do this simulation. So this has been covered by Nishant. I'll just give a brief recap and summary. So these are the fluid equations that we solve. The first is the continuity equation of the mass conservation equation, which implies that the total mass is conserved. So, and defines a rate of change of density with the flux of the density. And you take a volume, the rate of change of the total mass inside the volume is equal to the flux of the mass leaving the sides of the volume. So there is no net mass produced or destroyed. That's what the first equation implies. The second equation is the standard force equation, the Lorentz force equation, which is the left-hand side is the total time derivative, and the right-hand side gives you the pressure forces and the Lorentz forces. The third equation follows from the entropy or the principle, or is a proxy for the energy equation. In an ideal gas, we know that pressure is proportional to k rho to the power gamma. And if you take the derivative of this, and after some manipulation, you will find an evolution of the pressure. So this essentially follows from the entropy condition. And the last equation is for the magnetic fields. It's called the induction equation, which relates how the magnetic field changes in response to the fluid flow. And what is really important about this equation is that we assume that the displacement current is zero. So there are no electric fields, and the del T term of displacement current is zero. On assuming that, I think Nishant must have said this, we get something called the induction equation. So we essentially solve these four equations, and keep in mind that the second and the last equation are vector equations. So there are three components in each for a 3D simulation. And this defines our evolution of the entire system. Now, solving this equation in this form is not very efficient. So what we do is we recast the equation in another form. This is called the conservative form. So these are the primitive variables: the density, the velocity, the pressure, and the magnetic field. They are called the primitive variables. And this form of the equations are called the primitive form of the equation. Now, this is called the conservative form of the equation, and the conservative variables are density, momentum, energy, and magnetic field. In the conservative form of the equation, we can recast the fluid equations in a form which is given on the top, this, where there is a rate of change of time plus a divergence of a flux equals to zero. Now this, if you remember, this directly follows from the, implies or relates to the Gauss's theorem. So if you take the rate of change of flux, so this is the divergence at a particular point in space. Now if you take a volume and do the surface integral over the volume, the rate of change of this quantity is equal to the flux of the quantity integrated over the surface. So what this again implies is, there is no, this quantity u is neither being created nor destroyed. The change of quantity of the u inside the volume is just related to the total flux of the quantity across the surface. And it can be shown that all the fluid equations can be recast in a conservative form. So this is the conservative form of the mass equation. This is the momentum conservation equation. And just to remind you, divergence of rho VV, VV is actually a tensor. And if you want to find, just to understand how that works, it's best to always break it up into components. See, so divergence of a tensor is a vector. And if you write it out in components and just do some simple math, you'll find that you have recovered. So divergence of rho VV gives you divergence of rho V VL plus V dot del V, and divergence of rho V gives you this quantity. And so you will see that you will recover the left hand side of this equation. So it's all consistent. So this is the momentum equation. But so this is also the stress tensor of the Lorentz force. This is called the stress tensor, the Maxwell stress tensor. And this is the energy equation where Xi is the total energy given here, when rho small e is the internal energy. This is the kinetic energy, and this is the energy due to the magnetic field. So what this equation tells you is the evolution of the energy related to the flux of the energy through a surface. And this is the continental equation. Now, all of these equations are actually underdetermined, and we need one more condition to solve these equations. And that is called the equation of state. And what we usually assume in this kind of fluid dynamics is the caloric equation of state, which relates the internal energy to the pressure and the density, as rho E is equals to the pressure divided by the specific heat minus 1. And again, what this essentially implies is the specific heat at constant volume is constant. And under this assumption, you can simply rederive the caloric equation of state. But again, that's too technical. So essentially what you have to remember is you solve the mass equation, the momentum equation, the energy equation, the magnetic flux conservation equation, and an equation of state that relates your internal energy to the pressure. So this is the basic standard equations. What you can see here is we have multiple partial differential equations, and all are coupled. The density appears in density and momentum all appear at different locations. So these are not independent partial differential equations. These are a coupled set of partial differential equations. And if you go to the classification of differential equations, these are hyperbolic systems in the standard elliptical, hyperbolic, and parabolic different PDEs. But there are hyperbolic PDEs, and you have to have special numerical schemes to solve these hyperbolic PDEs, which I will discuss now. So one way to solve these equations is using a finite difference schemes, which I was mentioning initially. You take your domain of interest and divide it up into small grids. And then U, for example, is a continuous quantity, but now you divide it into grids. And at the center of the grid, you define an average quantity of the U, which defines the U over this spatial region. So U varies in steps depending on the resolution of the grid. And you can discretize the derivatives. I'm sure this is something that you've all done. There is a mistake here. This was swapped. This is the centered derivative, and this is the forward derivative. My mistake. And this is second order accurate and first order accurate. Anyway, but I'm sure you've all read through it. So this is, for example, you can have several discretizing schemes. This is the centered spatial derivative. Let me change it here itself. Yeah. So this is a centered spatial derivative. This is which is second order accurate. This is a first order accurate. And in this kind of simulations, we can go up to many orders of accuracy. For example, this is the form of the derivative scheme of the first derivative, which is 6th order accurate, which I've taken from the pencil code. So essentially what we do is we take this continuous quantity and discretize it on the grid, and then we discretize the entire fluid equation over here, and then solve them on the discretized gates using various kinds of numerical schemes. Another way to do it is we do not discretize quantities in terms of grids with a value at the center, but we discretize in terms of volume. We do discretize, but what we do is we discretize it into cells, and each cell is considered to have an average quantity. And the average quantity does not necessarily represents a quantity at the center, but we do average over the entire region. For example, we take the ith cell and we replace the value of the u in the ith cell with the average from I minus half to I plus half. So these are the cell interfaces. So this is I plus 1, and this is I plus half and I minus half. So the extent of the cell lies between I plus half and I minus half, and we replace the value of this quantity u by an average over the entire region of the cell. So this is called a finite volume, where then we replace the continuously varying quantity u with volume averages at the centers of the cell. So this is the kind of simulation that I do, because as you can see, if you do a spatially discretized simulation, a scheme of simulation, what you end up doing is you take derivatives, and if there are sharp discontinuities, these derivatives will explode, because a derivative of a discontinuity is infinity. So, but the good thing about this scheme is, as I will show you for the finite volume scheme, you do not have to take derivatives anywhere, because you work in this conservative form of the equations, which has derivatives. But since, as I said, now you replace them as volume averages, you integrate over the volume. You convert the divergences to fluxes across the surface. So for example, if you have the divergence here, you can easily find the flux on these two surfaces and find out the evolution of the quantity u in terms of the evolution of the fluxes. So there are no differentiations involved. And that is why if you have discontinuities in your fluid, then your solution does not become infinity or blow up. Your solution is stable. And that is one of the main advantages of this kind of schemes, of the finite volume schemes. So just to give you so this might get a bit technical, and let's see. So this is the conservation equation in 1 dimensions, as I had showed you. So I had showed you the previous case of the 3 dimensions, but for simplicity, let's take 1D. So rate of change of time plus a divergence of flux, which is just the del f del x. Now we integrate over both time and space. Now, by simple Gauss's theorem, in the integration over space of this quantity is just the difference of fluxes, right? Because that's what the Gauss's theorem tells you, that the divergence of a quantity is an integral. The divergence of a quantity is just the difference of sum of the total fluxes across the surface. And I minus half, the normal to it is on this side, and the flux is going here, and that's why then there's a negative sign. Fine. And we replace the spatial integration over the del u del t with this definition. So we replace the del u del t with the volume average, or the rate of change of time of the volume average. And now we can do the time integration. So if you do just a first order linear integration in time, what we can replace this as just integration delta t over this range of tn and tn plus 1 and divided by delta x. So what we have accomplished is we have now this rate of change of time. We can just do a simple decomposition of tn to tn plus 1 varies as un plus 1 minus un divided by delta t. Take everything right hand side, and this is what you get. So what you have essentially accomplished is you follow the time evolution of this quantity n by just simply finding out the fluxes at the interfaces. Now, this is the challenging part. The fluxes at the interfaces are not easily available. So at times, so if you look at this equation, there is a time integral involved here. Okay, so the fluxes, here the fluxes are at time tn, but then I have taken it out of the integration, so I have partially integrated them. So this is somewhere in between n and n plus 1, and we call it n plus half. So at the initial start of the simulations, we already have the fluxes at time tn. What the main job is to find the fluxes at the cell interfaces at the n plus half stage, so that we can follow this evolution of the equation. This is just to give you an example, because this is a more involved mathematics involved in it. I'm not going into the details, but this is called the Godunov scheme of finite volume, where you take the fluid systems, describe them in terms of a finite volume scheme, and then by integrating over the fluxes, you find out the fluxes at the interface to evolve the system in time. And that is called the Godunov scheme. So as I said, the main problem of the Godunov scheme is finding out the fluxes at the cell interfaces and how they evolve in time. And this is something that I will briefly talk about in next. This is called the Riemann problem. So at Tn, or the initial time step, we know the value of the fluxes here. What is the value of the fluxes at the intermediate step, which we can then replace in this equation to find out the evolution of time of u? That is the challenging problem, and that is called the Riemann problem. I'll talk about it. So the basic principle of the Godunov scheme, as I said, was it is based on volume integrals. So there is no explicit computation of the derivatives, and hence it is much better for handling discontinuities and shocks in a system. So shock is when there is sharp change in the pressure of the system, and then such sharp discontinuities can be handled. These are conservation relations, so the basic assumption is from a conservation point of view, so that mass and momentum are not created and just are related to the total fluxes. It is accurate up to the second order, and thus for similar finite difference schemes that is accurate up to second order, there is no difference. But finite difference schemes can go to much higher order, sixth order, for example, as I showed you earlier. But the Godunov scheme going to higher order is more challenging. And the primary source of errors in the Godunov scheme are the approximations introduced in computing the fluxes of which are called the Godunov fluxes. And so this is the main problem. So this is how you compute the Godunov fluxes, which is called the Riemann problem. So if I go back to the previous states, when you discretize the system and replace the quantities with volume averages, what you end up doing is you have some discrete states. For example, this is like filling water in different levels. So each of these, so in a truly continuous system, it might have varied like this, but now you discretize it as something changing for each length cells. So at the interface, what this interface sees is on its left-hand side, there is some value of the fluid variable. On its right-hand side, there is another value. There is a discontinuity. So the main basics of the Riemann problem is this. So given this problem, where the variable ux has this initial condition, it is something on the left-hand side, something on the right-hand side, how do you solve the evolution of this flux conservation equation? And there are mathematical tools to do that. Again, I'm reminding you that all the fluid variables here are the conservative fluid variables, which are the density, momentum, and then the energy, as opposed to the primitive, which is density, velocity, and pressure. So these U's are the conservative fluid variables, which can be density, momentum, and energy, and the magnetic field. And there are mathematical tools devised to solve this equation in this kind of a basic initial state, and that is called the Riemann problem. I will not go into the details of it, but this is what comes up when you do simulations. And again, just to give you a flavor of what this Riemann problem is, what we do is we start off with this equation here, which is the rate of change of time plus the flux, derivative of the flux. We transform it into a matrix equation, rate of change of time plus the Jacobian plus the spatial derivative of the variable W. And what we essentially end up doing is finding, turning up into a matrix. So for example, in 1D, the variables, okay, here I have presented them in the primitive form, which is the rho, the velocity and pressure. And this AW matrix for the fluid equations would look like this. What we have to do is find the eigenvalues of this matrix. And the eigenvalues of this matrix defines speeds of different waves that are characteristic of the particular system. For example, in this particular system, the three characteristic speeds are the velocity of motion, the velocity of motion plus sound speed, and velocity of motion minus sound speed. So sound speed is one characteristic wave, but the three different waves, three different speeds with which information can travel in the system are these waves. And once we have this, we can find out the solution as it progresses along these three different directions. And the total solution will be a sum of all the eigenvectors. So each of these eigenvectors will propagate along these three solutions, and they're all independent. And the total final solution will be a sum of the eigenvectors. So again, a bit complicated, but any of this Riemann problem, you will find this characteristic decomposition of the problem along three different solutions, finding out the eigenvectors, and some of the eigenvectors are all independent to find the total solution. That is essentially the solution of the Riemann problem. It sounds simple in 1D, but when you have multiple dimensions with multiple coupled equations, you cannot solve this analytically, or you can up to an extent, but it is very cumbersome. So we have to make several assumptions. And one of the typical common assumptions is we do not solve for the full eigenvalues. We just find out the maximum eigenvalue and the smallest eigenvalue, and approximate these different characteristic solutions with the maximum wave speed and the smallest wave speed. And that is how we evolve the fluid simulations. Again, I'll not go into the details. So there are several approximate Riemann solvers that we have to use. And this is the place where errors are introduced in our computation. The typical approximate Riemann solvers are, for example, are called the HLL, HLLC, rho, etc. HLL standing for Harten-Laks-Bandlia, HLL, and the C with the contact discontinuity. So basic problem of the Riemann solution is you have a discontinuity across the cell interface. We can, of course, go brute force and solve these equations by matching the shock jump conditions, because it's essentially a shock, but that is very cumbersome to do, and we have employ approximate relations to solve this Riemann problem. So once you solve the Riemann problem, there is another piece of thing that you can do. So as I said, in this volume, the definition, or in this way of defining things as volume averages, what you end up doing is you assume things inside this cell are just represented by by just one spatial volume average quantity. And so you might naively expect that within this entire cell, the volume average quantity is just constant. So you have discrete evolution of this. However, there are higher order ways of improving upon this. You can assume that between these two cell interfaces, this volume average quantity is varying linearly with time, or linearly with space, not time, sorry. Or we can have higher order interpolation schemes. So these are like interpolating between these two interfaces. They're called interpolation schemes. Now they're called, for example, this is third order accurate, the piecewise parabolic, etc. So this is also another level of sophistication we always use, that between these two cell interfaces, we do not assume a constant description of the fluid variable, but it is varying with slope. As I show in the next session, the various numerical schemes we use, all of this will come into play, and I'll discuss the various choices. And for example, we assume a polynomial, and the order of the polynomial defines your level of approximation. For a linear order, you just consider up to this term. For a parabolic order, you consider up to here, which is the ppm scheme, etc. So this is the standard flowchart. We initialize all the fluid simulations at different grid points at t equals 0. We find out the fluxes at the edges. So given a volume average quantity here, we interpolate the fluxes at the edges using this polynomial expansion. So that is the reconstruction step. Then we solve the Riemann problem. Now that we have the fluxes at these edges, so there is a flux here and flux here at each interface. Now, as we have this, then we solve the Riemann problem here. So we can reconstruct the fluxes at the edges. Then we have the Riemann problem, and we solve the Riemann problem. That is, if you have this to discontinuity of this two at this interface, how will the value change at this point with time? So that is the Riemann problem. You solve the Riemann problem. Then we integrate in time using the Godunov flux scheme. You check for output, and then you keep on going until there is a condition to stop. So in the next 5 minutes, maybe, before I take questions, I'll briefly give you some examples of the different kinds of simulations to give you a flavor of the capacity and the complexities of different simulations. So this is a video of the illustrious simulations done by people at Harvard. This is till date one of the largest simulations of a part of the universe. This is not an exact representation of the universe, but one of the largest large-scale simulations of galaxy evolution. I'll talk about the figure on the top later. They have improved upon this and done illustrious next generation simulation called the illustrious TNG, but at its time it was the largest simulation. So all this filamentary structure that you see are actually galaxies. So these are galaxies clustering due to gravity, and this is a particle kind of simulation. So each of these galaxies are composed of several particles of stars, and they also have a fluid description of them. So now you can see as the galaxies accrete and galaxies come closer together, they have central supermassive black holes. The central supermassive black holes then start accreting gas. Part of the gas falls in, part of the gas gets too hot and then escapes out of the galaxy as outflows from jets. You can see there was an explosion here. And all of these galaxies then start throwing out material to large scales. And this is what regulates the evolution of our galaxy. So you can see the basic thing is you can see this filamentary structure being predicted by simulations. Now these are actual observations of galaxies going back with time, observed by the SDSS observing facility. And you can see as you are looking back in time, so as you move away, you are essentially looking back in time, you can see this filamentary clustering structure. So this filamentary structure have been predicted analytically. They have been shown by simulations and also by observations. This is the power of simulation. This is a very highly complex nonlinear phenomena, and you cannot do them analytically. Analytically, you can at best go up to linear order perturbation theory. But to understand a much deeper to higher order efficiency and to actually match with observations, you need to do simulations like this. And this is a very expensive simulation. It took 21 million CPU hours, huge amount of time. So these are some of the simulations that I have been doing. For example, in the previous case, I showed how the supermassive black hole starts exploding in the large scale system. So what we've been doing is understanding how these small black holes, how they affect the gas within the galaxy itself. So this is a 3D simulation. You can see the 3D volume rendering of jets coming out from this dense, clumpy gas distribution of the galaxy, which is a rendering of this. And this is a 2D slice of the simulation. This is the X and Z axis to the midplane. And as you will see, this is a different, so here the jet was slightly oriented along the plane of the galaxy. And as a jet, so this is a jet that's coming out from the central black hole. And as the jet goes and interacts with this gas, it is throwing out this gas from the galaxy. You can see small comet-like structures rising out and moving out with like cometary tails. And all of these are nonlinear phenomena. So you cannot do them linearly. And we have to do them by solving the fluid equations. And so these are jets from supermassive black holes at centers of galaxies. I'm not sure if people have talked about this to you, but this is an example of a jet from a supermassive galaxy. This is the Centaurus A, where you can see this jet coming out of the central disk of galaxy and this wisp of bubbles. And again, a few other simulations. So this is what, by this simulation, what we are trying to show was how this jet strongly interacts with the galaxy of gas of the galaxy. So this cloud-like filamentary structure are within the core of the galaxy. These are molecular clouds that are several parsecs in size. But what is the main point of interest of this is not just to have this pretty picture, but to understand how the temperature and pressure evolves, and what is the implication of having this high temperature hot gas embedded inside the galaxy, and how does it impact on the galaxy? So these are the kind of questions that we try to answer. So these are simulations on the galactic scales. Now I will come back to smaller scales. So these are simulations not by me, but by Romanova et al. Of accretion onto neutron stars. So if you have a neutron star at the center, you can, it can accrete matter from a nearby star, and the matter flows along the, so these are like a dipolar magnetic field, much like the Earth. The matter goes here beyond a certain point, it cannot penetrate the magnetic field and gets channeled onto the poles. This is very similar to how you see auroras in the North Pole and South Poles. And this is an example. So there are various kinds of instabilities that can occur. For example, in this case, the matter is leaking through this side. So in this case, the matter could not penetrate the magnetic field, but here the matter can penetrate the magnetic field due to an instability called the Rayleigh-Taylor instability. And instead of going to the poles, it's actually going to the equator. So different kinds of parameters of simulations can give you different results. And that is what we try to do. By changing different parameters, we try to see how the fluids react. And this is something that we cannot predict beforehand. And again, some of the times we don't really model astrophysical scenarios. We just find out the evolution of fluid instabilities themselves. In this particular case, what I did was this matter, as it goes to the poles of neutron stars, it gets accumulated and confined by the magnetic field. But as the matter is confined, it can have these instabilities. I'll play the movie again. So this is a chunk of matter over here, a small chunk. And you can see these finger-like protrusions. These are something called the pressure-driven instabilities. And this is similar kind of instabilities that you find in tokamaks, which are plasma reactors for fusion reactors. And it is very difficult to confine the plasma in the fusion reactors by magnetic fields because of this kind of instabilities. And similar mechanisms operate also on neutron stars. So the world of plasma physics is not just confined to terrestrial objects, and astrophysics themselves is not just has a wide variety of application of different areas of physics, from plasma physics to condensed matter physics. And in terms of numerical simulations, we try to see how these different physical processes interact and then affect the evolution of the system. So I will stop my talk now, and I would ask you to raise hands, people who have questions, and then we can maybe take, I will unmute you, and then we can see from there. Okay, I have a few hands up. Give me a second. Okay, so Junik Sengupta, I'm unmuting you. You can ask your question.
Good morning, sir.
Good morning.
So my question is, in those conservative variables, what does that variable epsilon actually defines, and how is that related to internal energy? Can you please redefine that a bit, elaborate it?
Sure. That's a very good question. Good. That means you've been attentive. So
Thank you, sir.
epsilon, right? This quantity.
Yeah.
Yeah. So this is the total energy, and rho small e is the internal energy. So the total energy is a sum of the internal energy plus kinetic energy plus the magnetic field energy. Now the internal energy is related by the laws of thermodynamics to the pressure. Okay, so epsilon is the sum total of all the energies, but how the internal energy comes, so because in the total energy you will have the internal energy, which is say a proxy of the temperature of the system, plus the kinetic energy because of the motion of the fluid itself, and there is a contribution from the magnetic field. But this internal energy, it's the way we connect it is through this caloric equation of state. So again, this goes into the basic formulation of thermodynamics, where in the caloric equation of state, we assume that the specific heat at constant volume is constant. So Cv is du dt, if I go into the details. And then this internal energy is just equal to Cv times T. Now T, you can take the ideal gas law, and that's replaced by PV, by gamma minus 1. So that's why you relate this internal energy to the pressure and gamma minus 1. Okay?
Okay, sir. Thank you, sir.
Okay.
So the point is, can I have a second question, if possible?
Okay.
Sir, the second question comes from the last part of your slides. You just said that while solving those Riemann problems,
yes,
in the Godunov scheme for finite variables, it is advantageous because it has volume integrals in place of differentials. So I just want to ask that why is it advantageous to have volume integral concepts to solve this apart from the differential concept? Does this because differentials create a discreteness in the solution?
that is right. Well, volumes also have a discreteness in the solution, but if you have the differentials in strong discontinuities, the derivative blows up, right? So that is why if you have a shock in a system, or if you have a sharp change or sharp gradients in your fluid variables, then the differential system will have an extremely high value of the differentials. So in that case, what people do when they do with the differential equation, they have artificial viscosity to reduce the gradient of the fluid variables. But this artificial viscosity is adding extra dissipation in your system, which is not unphysical. But this problem does not arise in terms of this Godunov scheme. It's not completely good, by the way, because in the Godunov scheme, the main crux is solving the Riemann problem. And in the Riemann problem, if you have these two states, if the discontinuity is very sharp, then some of the approximations in the Riemann problem also breaks down. But the Riemann problem is much better in handling these discontinuities and shocks than the normal differential schemes. Okay?
Okay, thank you, sir. Thank you.
So next question is Madhusudan Purohit. But I will just ask you, I'll just read out your question and then say this. So how about boundary conditions? So I will discuss this in more detail in my next session. So next hand up is Yashodhan Joshi. Yashodhan, if you want to ask your question.
Hello, sir.
Hello.
Sir, I wanted to ask that when running these simulations, are some kind of central database system used to store the states of individual elements in the system, or the states are stored locally on computing nodes and they talk to each other when they require states from the other nodes?
So can you just repeat the question in the sense of what do you mean by store the elements?
Elements as in if in particle simulation the states of the each particle or
yes, okay, so
kind of
yeah. So for example, in the particle simulation, as you said, if we have 1 billion particles, then we divide them into chunks of say 1,000 particles in one processor. Now in each processor, the local evolution of the particles are stored in that processor itself. But sometimes if say particle 100 is lying next to particle 101, and these two are in different processors, then the processor A has to know the conditions of particle 101, because the particle 101 will affect the evolution of particle 100. That is why we need to have this transfer of information from one processor to another processor. So that is called the message passing interface, MPI.
Thank you, sir.
Okay. So the next is, give me 1 second. I'm just reading through the chat to see who has questions here. I will avoid questions that are extremely general. For example, questions on Big Bang and singularity. These are not relevant to these lectures. Arjun Don, he has a question but has not raised a hand. Soumya Samrat Mondal, do you want to ask the question?
Yes, sir.
Okay.
Hello, sir. Yeah, my question was that as suggested by a simulation of the universe after the Big Bang, was there any point of time when gravity might have overtaken over that expansion of the universe as it was predicted by the simulation?
Yeah, so these kind of simulations do not really go over such large scales where you can see the effect of gravity to quench the simulation. So what they assume is a standard standard metric and expanding universe. Okay, and
Yes, sir.
a standard model of the universe, and then that is
Okay.
the basic assumption of the universe, and then they follow the evolution to match the templates as they find out the evolution of the galaxies. Then at the end of the simulation, they match the templates of the results with the observed results. So they are by design to reproduce the current state of simulation, which is an expanding universe. So
Okay,
there are some simulations done where they change the cosmology of the simulation to have an extra dark energy, dark matter, etc. that can contract. But those are not the simulations that I discussed.
Okay, sir. Thank you, sir.
Okay, I can see one more hand, Ganesh Prabhu.
Hello,
Do you
sir.
want to ask a question?
Hello, yes, sir. Could you hear me?
Yes.
Sir, based on the electronic way, that is, we have got a microprocessor speed as maximum up to 3 gigahertz.
Mm-hmm.
But you are using several microprocessors to do the simulations.
Yes.
But if we go for photon-based computers, then can we increase the speed of simulation?
Can you repeat the last part? If you go for what? Because you broke up.
If we go for, instead of electronic means, if we go for photon-based computers.
Oh yeah. So that you're talking about completely new technology. Yes, of course. We can.
Yes, sir.
We can of course speed up computers, but this is not a question relevant for fluid simulations. This is true for any kind of simulation, any kind of computational work, right? So yeah, we can definitely have a speed up, but this is not really relevant for this fluid-based simulation that we say. Thank you.
Okay, thank you, sir.
Okay, so I don't see any hands raised, and I don't see in the chat as well questions that are directly relevant. Quantum computing not relevant for this lecture. And Arjun Don, what is the reason behind the instability of a neutron star so that the particles can penetrate through the magnetic field and reach the equator? Okay, that's a very interesting question, Arjun. I see that your mic is not working. So Arjun's questions relate to the last part. I think this is the last question I'll take because I'm beyond over the time. So based on this simulation, where it was shown that the streams of plasma is actually penetrating. So this is a standard fluid instability called the Rayleigh-Taylor instability, where if you have a heavy fluid on top of a lighter fluid, and there is external force of gravity, then the heavy fluid forms these finger-like protrusions and enters into the lighter fluid and in the system. Now there is no heavy fluid, light fluid here, but what you have is this extra pressure by the magnetic field, which simulates the effect of a lighter fluid. So this is a Rayleigh-Taylor instability. You can read up on standard fluid text that is taking place here, and this is very well documented in many standard basic fluid texts. Okay, so I will stop the question answer session now because I have gone over time. We will join back today in the afternoon, and then I will discuss the some of the codes that I use. I'll give you a demonstration of how to use the code, how to install it, and show you some basic examples of running the simulations. So I'll see you, some of you, in the afternoon. Thank you.